Hello, everyone. In this video, I'm going to be going over my approach to problem 23 in chapter 8 of the Fundamentals of Mass and Heat Transfer textbook. So this problem says that fluid enters a tube with a flow rate of 0.02 kilograms per second with an inlet temperature of 20 degrees C. The tube, which has a length of 8 meters and a diameter of 20 millimeters, has a surface temperature of 30 degrees C. Ask us to determine the heat transfer rate of the fluid if it is water, and if it's a nanofluid, where we can find the properties of it in example 2.2. So to start with, I wrote down all the given values. The properties of water is actually in table A6, not A4. I miswrote that down. It has properties uh, such as dynamic viscosity of 855 times 10 to the negative 6 Newton seconds per meter squared. Uh, Conduction coefficient 0.613 watts per meter Kelvin, specific heat of 4179 joules per kilogram Kelvin, and a Prandtl number of 5.83. The nanofluid, according to problem 2.2, a density of 1146 kilograms per meters cubed, dynamic viscosity of 962 times 10 to the negative 6, same units as before. Uh, Conduction coefficient of 0.705 watts per meter squared Kelvin, specific heat 3587 joules per kilogram Kelvin, a thermal diffusivity of 171 times 10 to the negative 9. This is needed in order to determine the Prandtl number, which is found by dividing the kinetic viscosity, which is the dynamic viscosity, over the density, all over the diffusivity, which will give us a Prandtl number of 4.91. So first thing we're going to have to do is find the Reynolds number. This is important for determining some thermal boundary conditions, such as the length of the thermal boundaries and the hydrostatic boundaries. So normally the Reynolds number is found by rho u, u being the flow rate, L over the dynamic viscosity. That can be fixed to having a mass flow rate using this equation, which is equal to 4 times the mass flow rate over pi d times the dynamic viscosity, which gives us a Reynolds number of 1489, meaning that the water is fairly laminar through this pipe. Uh, Next, if we want the thermal boundary distances, the hydrostatic is equal to 0.05 times the diameter times the Reynolds number, giving us a value of 1.49 meters. The thermal boundary distance is equal to that. We just also multiply the Prandtl number, giving us a value of 8.68 meters. And then, unfortunately, so normally with the fluid, if we got a Prandtl number of greater than 5, we're able to use the Hausen correlation in order to determine what the Nusselt number is. The Hausen correlation is this equation here, 8.57. However, as stated, the nanofluid has a Prandtl number of less than 5, which means that we're not able to use that. And instead, if we want to properly evaluate and compare these two fluids together, we got to use this monstrosity that is equation 8.58. I am very sorry. I wake up at night and dread having to think about using hyperbolic trigonometry. But unfortunately, this is the equation that we got to use. In order to follow through with this, we need the Great's number, which is equal to the diameter of the tube over the length of the tube times the Reynolds number times the Prandtl number, which is equal to 21.7 in the case of the water. Plugging all that in will give us a Nusselt number that I unfortunately forgot to write down. It is no doubt very high. You Give me a second. I'll be able to pull out my calculator and verify what the number that I found was. Yeah. Okay, so I found the value. It's 4.98 for the Nusselt number. We can plug that into H, the Nusselt number times K over the characteristic length, which is this case D. That gives us a convection coefficient of 153 watts per meter squared Kelvin. Now, in order to find the outlet temperature, we need to use this equation, which is equation 8.41b. This is the equation that we use if there's a constant surface temperature, which is in this case. We plug all those values in. Ts minus T outlet over Ts minus T inlet is equal to the exponential of the perimeter times the length. So the surface area over m dot Cp times the convection coefficient. And this will give us a final outlet temperature of 26 degrees C. So if we know the inlet temperature and the outlet temperature, that gives us the delta T. So in order to find the heat that entered, we simply take the mass flow rate times the specific heat times the delta T, which gives us for water a heat entrance of 501 watts. Now we're going to go through this all again for the nanofluid. This is simply going to be, for this, you're going to take all the math that you did before and plug in the new values. So the Grates number will be different, which means that the Nusselt number will be different. So the H will be different and the outlet temperature will be different, but you just follow through. I didn't want to write the Nusselt number equation again, so I just did them all and wrote down all the key values. Got a Reynolds number of 1324, boundary distances of 1.32 meters for the hydrostatic, and a thermal boundary distance of 6.48 meters, a Gates number of 16.2, a Nusselt number of 4.68, a convection coefficient of 165, and an outlet temperature of 26.9 degrees C, giving us a heat flow rate of 492 watts. Now, it can seem kind of weird that the that the heat flow in the nanofluid is less than that of the water, even though it rose to a greater temperature. That's understandable considering that the water just has a higher specific heat and therefore has a higher thermal mass. It takes more energy to heat up the water than the nanofluid. So this has been my approach to this problem. I hope that it was very useful, and I'll see you in the next video.